Muted. Okay, Assalamualaikum and good afternoon. Okay. Sekejap saya tengok ni kan. Sekarang ni mic dah lain dia punya ni. Saya jadi macam sekejap. Confused. Apa saya nak tekan? Okay, so we have now 29 students. One more student is missing. Let us see who is missing. Pradip ada. MNOPQRS. Seri tak ada. Where is Seri? Okay, Seri is missing. Okay, so let us start now. Continue with topic. Apa dia cakap ni? Aduh. Just tap on different window. Can you see the slide? Okay. Okay, so we have done with the universal shift register. Okay, and then bidirectional shift register. Today we continue with another type of counter. Okay, now shift register counters. Shift registers can form useful counters. Wait, let me make it bigger. Okay, shift register can form useful counters by recirculating a pattern of zeros and ones. Okay, two important shift register counters are the Johnson counters and the ring counter. Okay, so now you look at here the diagram for the Johnson counter. Okay, in this diagram, okay, Johnson counter can be made with a series of D flip-flop. Okay, so you see in this diagram, this is a 4-bit because you have 4 flip-flop. Okay, and then you look at here, you have FF0, FF1, FF2 and FF3. Okay. Ya. Oh, kejap Kejap. Apa ya? Nenek. Okay, sorry about that. Okay, now look at this Johnson counter. If you can see, this is for 4-bit. You have FF0, FF1, FF2 and FF3. So you look at here, D0 here is connected to Q3 bar. Or you can say here Q3 bar, okay, which is on the last flip-flop here is connected back to the FF0 to D0. Okay, and then Q0 is connected to D1, Q1 is connected to D2, Q2 is connected to D3. Okay, and then all the clock are connected to, all the flip-flop are connected to one clock here. So this is synchronous or asynchronous counter. Okay, so this is synchronous counter. And then you look at here, there is no bubble. So this is positive edge. Yeah? You look at the positive edge of the clock. Okay, so or with a series of JK flip-flop, you can also design this Johnson counter using JK flip-flops. So now at the bottom here, you can see the diagram. Okay, using JK flip-flop, you have J0, K0, and then the last flip-flop here is J3 and K3. Here Q3 and Q3 bar, okay, Q3 and Q3 bar fed back to the J and K inputs with a twist. So if you look at here, Q3 bar is connected to J, okay, and then Q3 is connected to K here, K0. So there is a twist here, okay, the twist is at this point. So if you redraw the circuit, okay, the same Johnson counter without the clock shown, so illustrates why it is sometimes called as a twisted ring counter. Okay, so this is the twisted ring counter. Just now remember Q3 bar is connected to J and then Q3 is connected to K. Okay. Okay, so this is the twist here. Okay, Johnson counter is useful when you need a sequence that changes by only one bit at a time, but it has a limited number of states. So there is 2n, where n is the number of stages. So the first 5 counts for a 4-bit Johnson counter that is initially cleared. Okay, so it's initially cleared here. And then when at the first clock, okay, you have here 1 0 0 0, and then second clock you have 1 1 0 0, third clock you have 1 1 1 0, and then fourth clock you have 1 1 1 1. So what do you think happened at the fifth clock? It will be shifted, okay? Remember, this is a 4-bit. So you will have so what are the remaining 3 states? You have 0, 1, 1, 1, and then you have 0, 0, 1, 1, and then the last clock here you have 0, 0, 0, 1. Okay. Okay, now look at the ring counter. Ring counter can also be implemented with either D flip-flop or JK flip-flop. Okay, so now you can look at here. Here is a 4-bit ring counter constructed from a series of D flip-flops. Notice the feedback. Okay, now you look at here. Q3, this is for 4 bits. Okay, you have 4 flip-flops, FF0, FF1, FF2, FF3. So Q3 is fed back into D0. Okay, and for all flip-flop, the clock is connected to one clock. So this is a synchronous counter. And then like the Johnson counter, it can also be implemented with JK flip-flop. Okay, you see here, this is for the JK flip-flop. You have FF0 until FF3 here. So Q3 is connected to J naught here, and then Q3 bar is connected to K naught. So if you redraw the circuit, okay, redraw the ring counter without the clock shown, okay, shows why it is a ring. So you see here, it looks like a ring. Remember just now J naught is connected to Q3 and then K naught is connected to Q3 bar. So it looks like a ring, right? Okay. So that's why you call this is ring counter. Okay. The disadvantage of this counter is that it must be preloaded with the desired pattern, usually a single 0 or 1, and it has even fewer states than a Johnson counter, where N, okay, is a number of flip-flops. So here is N equal to 4. On the other hand, it has the advantage of being self-decoding with a unique output for each state. So now we look at here, the ring counter. So a common pattern for a ring counter is to load it with a single 1 or a single 0. Okay, you only load one single bit, either 1 or 0. So the waveform shown here are for an 8-bit ring counter with a single 1. So now you have here Q naught, you have here, you look at it, it's positive here, and then Q1 shifted, okay, and then Q2, this positive is shifted, and then you have this kind of timing diagram for the ring counter. Okay, so the last Q7, you see the Q7 which is at the 8th flip flop. Okay, you see the 1 is shifted there. Okay, so now shift register application can be used to delay a digital signal by a predetermined amount. Okay, so example here, an 8-bit serial in serial out shift register has a 40 megahertz clock. What is the total delay through the register? How do you calculate that? Okay, how do you do that? Okay, let's see the answer. First, of course, because this is in hertz. The question is the total delay. Delay normally is in time, right? Okay, in second. So you must convert this into second first. So the delay for each clock is 1/40 megahertz. Okay, and then this is equal to 25 nanosecond. So for the whole 8-bit serial, in serial up, what do? You multiply with 8. So there is a delay of 200 nanosecond. Okay, so remember when the question asks the time or total delay, is always about time. So time is in second. So if the question asks in hertz, you must convert that to second first, and then you multiply with how many flip flop and so on. Okay. So see here, this is the data in, because you have 8, okay, see 8 bit, so meaning you have 8 flip flop. Okay, so now this is the delay, 200 nanosecond. Okay, so this is the another application, a UART or universal synchronous asynchronous receiver transmitter is a serial in parallel converter and a parallel to serial converter. Okay, so you can see here data goes into the receiver shift register and then goes into the receiver data register and then goes to buffer and then goes to bus, data bus, and from buffer also is it's like what bi-directional. Okay, you can see here, this is transmitter side, okay, and also the receiver side here. Okay, and then UART are commonly used in small system where one device must communicate with another. Parallel data is converted to asynchronous serial form, okay, and transmitted. The serial data format is, you can see this is in serial data where D0 goes in, okay, and the data must always have stop bit, start bit and stop bit. Stop bit to differentiate between one signal with another signal. Okay, otherwise it may be overlapped, right? So you must have time. This is called the stop bit. And then keyboard encoder. The keyboard encoder is an example of where a ring counter is used in a small system to encode a key press. Okay, so the 274HC195 shift registers are connected as an 8-bit ring counter preloaded with a single zero. So as the zero circulate in the ring counter, it scans the keyboard looking for any row that has a key closure. Okay, when one is found, a corresponding column line is connected to that row line. So the combination of the unique column and row lines identifies the key. So you can see the schematic shown in here. Okay, this is the schematic for the simplified keyboard encoding circuit, the whole system. It has clock and then flip-flop here. Okay, this is where the key board here, when you press, okay, it goes into the row and the column, and then it shows what is the value and so on. Okay, now key term. What is register? One or more flip-flop used to store and shift data. Okay. Stage is one storage element in a register. Shift is to move binary data from stage to stage within a shift register or other storage device, or to move binary data into or out of a device. Okay. And then load is where to enter data in the shift register. And then bidirectional, having two directions. Okay, in a bidirectional shift register, the stored data can be shifted to the right or to the left. Okay, I think that's all for today. Okay. Any question do you want to ask? Tidur dah diorang ni. Hello. Okay, you don't have anything to ask?
Doctor, I want to ask.
Ah.
The exam, how the question are going to come out for the
Wait, I cannot hear you. Okay. Okay.
in the exam, how the shift register question is going to come out?
Shift register. Oh. Shift register is either you have to draw the timing diagram, okay, or you have to list like shift to the right, shift to the left, okay, and then some normally short answer, for example, okay, list out all the type of shift register, for example, serial in, serial out, and so on, that kind of question.
Oh, okay.
Okay.
Doctor.
So your test will be next week, on Friday, Friday night, like 8 to 10, something like that. Okay, make yourself available. And then I have set the question. I think it's easy question because most of the question for flip-flop, you have to draw the timing diagram, right? So I want to know whether you have computer or you use handphone.
Computer.
Do you have computer? All of you have computer or you don't have computer? At least, desktop or uh, notebook. All of you have computer? I want to know how many of you use only handphone. Because you need to draw. So I don't want you to waste time on redraw the clock, because if you just draw the answer, I may not know the age. Is it at positive age you draw that answer? Is it negative or positive age, and so on? So that's why I want to know, because one way you can do.
Betul betul.
Pula dah. Dengar tak? Kenapa dia hilang? Okay, so one way you can do, if you use your computer, you can copy the diagram of the timing diagram in the question, and then you paste in Paint. Okay, you paste in Paint, because Paint you can draw the line. You use ruler. You can draw line, so you can draw the timing diagram in there. Or otherwise, if you have printer, you can just print and then you can draw on that question paper. Okay? Faham tak? Macam mana nak buat kalau you have, because you will get that kind of question that you have to draw the timing diagram. That's kind of question asked for flip-flop normally. Okay? Ataupun you can draw using document. On document you can draw tak? Tak tahu, sebab kalau biasa dokumen dia ada juga yang boleh macam ruler tu you can draw, tapi I'm not sure. Tapi if you want to redraw balik the clock, then we waste your time, because when you want to draw the clock and then you want to draw the signal, the input signal, for example for D flip-flop, for J, K flip-flop, and then you waste time. Tarik, tapi word I'm not sure. You can do it or not. Can you do that? But in PDF you cannot do, I think. Pukul 8 suku, saya set 8 suku sampai pukul 10 lebih. Tak apa, nak tidur awal ke? Okay. Don't forget to tick your attendance. Okay, any more question you want to ask? It covers from the adder, So remember, you have to study adder, subtractor, and then comparator, and then encoder. That kind of question. You have done in class or in exercise or in the lab. Okay. So adder. So half adder, full adder, subtractor, half subtractor, full subtractor, and then comparator. Remember, comparator, either you want to use design using 2 bits or 4 bits and so on. Okay, comparator, and then what else? Encoder. Okay, design using encoder or design using marks. Remember that? How to use? And then what else? And then the difference between latch, flip-flop, and then in the symbol, what is the difference in the symbol for latch and flip-flop? Can you tell me?
What that tu?
Huh?
What the questions?
What is the difference between latch and flip-flop in a symbol? Normally kan you draw the symbol, the square there or rectangle, and then for example if D flip-flop, you have D. Okay, or D latch, you have D. Okay, what the difference between flip-flop and latch? You look at the clock, right? At the clock normally you have a small like triangle there. Okay, so that differentiate whether it is a latch or flip-flop. So go back and look at the notes. Look at all the symbol And then what else you have learned? You learn about SR, latch, and then flip-flop, and then D, latch and flip-flop, H trigger, JK flip-flop, T flip-flop. So make sure you know how to draw the timing diagram given all those. And then master and slave. You know what is master and slave? What is master and slave? Okay. Okay, now let us look at this YouTube. This is referring to master and slave. Can you see this? Memang saya bagi selalu 5 minit awal kan? Okay, test 1 pun saya bagi hari tu awal. Unless you masuk awal lambat. Saya bagi awal. Memang untuk awak nak print, mana dah tahu nak download dulu. Okay, saya bagi extra selalu. Okay? Okay, now look at this master and slave flip-flop. Pay attention, this is important.
In this presentation, we will see the behavior of master-slave D flip-flop. And for this, I will draw few waveforms, the output waveforms here. And once I have the waveform, I will draw few important steps.
Share screen, Doctor.
Share the screen tak nampak Oh, okay, kejap. Suara dengar? Mana pergi pula? Nampak tak ni? Okay.
In this presentation, we will see the behavior of master-slave D flip-flop. And for this, I will draw few waveforms, the output waveforms here. And once I'm done with the waveform, I will draw few important results. Like what is a glitch, how to remove a glitch, what is the relation between the master-slave flip-flop and the negative edge trigger flip-flop. For that, we have to find out QM. QM is the output waveform of your master flip-flop. Similarly, we will find QS, the output of the slave flip-flop, QP, the output of the positive edge triggered D flip-flop, and finally QN, that is the output of the negative edge triggered D flip-flop. We have to find all these four waveforms by using the truth table of the D flip-flop. But before actually going into this, let me first explain you the signal I have already drawn. I am having my clock, the green one is my clock, and the T signal is the input to the D flip-flop, and you can see I have taken a random signal. It is not that much random because it actually covers all the possibilities. Now what are the possibilities? The first possibility I can talk about is when the clock is low but the signal is high. Here you can see. Similarly, if I talk about the second possibility, then the clock is high and also the T signal is high. In the same way, it covers all the rest possibilities. That's why I have taken this signal for the analysis purpose. So let's go into this, and we will start first by discussing this master slave operation, what it is. You have already learned about these things in a separate presentations when we were having the discussion on the JK flip-flop. So master slave flip-flop consists of two flip-flops. The first flip-flop is called as the master flip-flop and the second flip-flop is called as the slave flip-flop. The most important thing to remember about a master slave flip-flop is the clock. The clock is given to the master, but the same clock is inverted by using a NOT gate and then given to the slave. The greatest advantage of this configuration is the toggling. We have toggling instead of race around condition in the JK flip-flop because we eliminated the effect of feedback there. Feedback was eliminated because when the master is operational, slave is not, because we have inverted the clock. Similarly, when the slave is operational, master is not. And this is all you have to remember about the master slave flip-flop. We will not go in much depth because we have already covered these things. So I will use the truth table for a D flip-flop, and if you don't remember, there is no problem. I will make one clock D, and the output is 2n plus 1. When the clock is low, whatever be the value of D, Qn plus 1 is going to be Qn, that is the memory state. And when clock is high, D is low, Qn plus 1 is also low. And when the clock is high, D is 1, means D is also high, output is also going to be high. This is because when D is 0, it means S is 0 and R is 1. And when D is 1, it means S is 1 and R is 0. So we will use this table to find out the value of QM. Now let's see what is the thing on which the QM is dependent. The first thing is the D signal that I have drawn here, and second thing is the clock. And this master flip-flop will be operational when the clock is high. So we have to check only for the pulses when the clock is high, or you can say the time interval when the clock is high. So let's start plotting our QM. QM is a 0 for this high pulse because D is 0. You can see from here, if D is 0, the output is 0. So I have QM 0 up to this point. And again, when the clock is high, you can see D is high. So QM will also go high till the next high pulse. And in this high pulse, there is something very interesting going on, which will cause the glitches. You can see D, our input signal, is low for a small time, and again it becomes high when the clock is high. So we are changing the input D signal in the high pulse. So what I have as QM is, it will be low initially, and again it will become high till the next high pulse. And when the clock is high again, D is high, so it will remain high for the next high pulse. And for this high pulse, you can see D is low, so it will again go low. And finally, here again we can see the input signal is changed during the clock. It is high initially, then it goes low. So our QM will also follow this. It will remain high initially and then it will go low. So this is the QM, and now we will move to QS, that is the output of the slave flip-flop. And you have to remember one important thing for the QS is the clock is inverted. We have to see for the time when the clock pulse is low. It means we have to see for this time, and this time period. we have to see only for the time when the clock is slow. It's very obvious because of this NOT gate. And also we don't have to see a D signal. Okay, we have to see QM because QM is acting as the input for the slave flip-flop. The D isn't, the QM. So we have to see QM and the clock when it is low. So let's try to get our QS. Initially, QS will be low because QM is low, and it will remain low till the next low pulse when the clock is low. And here you can see when clock is low, QM is high. So our QS will also become high till the next low pulse. And again, for this low pulse, the QM is high, so it will remain high. And for this time, when the clock is low, you can see QM is again high, so it will remain high. And for this low pulse, QM is low, so finally it will go low. And for this low pulse, QM is low, and it will remain low throughout. So this is my QS signal. You can see it is very easy to draw once you have the truth table for the D flip-flop. Now we will try to have QP. That is the output of the D flip-flop simply, not the master slave one. It is the output of a simple D flip-flop when the input is given, and the input is this D. We don't have to do anything with the QM. It's only for the slave. So the input is D, and we have to check, or we have to actually consider the change in the circuit when the clock goes from low to high. It means all the rising edges. This is the positive edge triggering, you already know, and we have to consider that the D flip-flop is working only when the clock goes from low to high. So let's check what we got in case of QP. I will change the color. Now you can see QP is low, and for this rising edge, again D is low, so it will remain low for the next rising edge. And for this rising edge, D is high, so QP will go high to the next rising edge. And for this rising edge, D is low, so it will become low and remains low for the next one. And for this rising edge, D is high, so it will go high, remains high. And again you can see for this rising edge, D is low, so it will go low. You can check from the truth table. When D is low, output is low. When D is high, output is high. So I'm not going to tell you this thing again and again. And for this rising edge, you can see D is high, so it will remain high. Finally, it will go low. So this is the output waveform for the flip-flop, which is positive as triggered, and the input signal is given here. Now finally, the last waveform is for the negative as triggered flip-flop, and it is very important. We have to draw various results from this thing. So let's try to find out the output of the flip-flop when it is negative edge triggered. We will consider all the falling edges, and I will use some different color for this purpose. Let's use white for this, and you will see some very good thing in a minute. I will just see these falling edges, and for this falling edge, D is low, so it will remain low for the next falling edge. And for this falling edge, this one, D is high, so it will go high. And again for this falling edge, D is high, so it will go high till the next falling edge. This falling edge, again D is high. Finally, for this falling edge, D is low, so it will go low. And for this falling edge, D is low, and it will remain low. So we are done with our 4 waveforms. Now let's try to find out few important things out of it. The first thing I will tell you is the glitches. You can see these sudden changes in the output signal. We call them glitches, glitches, and they are definitely not desired things. And the very important point that I'm going to make is, you can see for the slave output, the glitches are removed. There is no glitches in the slave output. That's why to remove the glitches, we use master slave flip-flop. And why the glitches are appearing in the output? because we are changing the input signal when the clock is high. So it is definitely not desired thing to do. The input signal must not change when the clock is high. This is not a common practice to do, because we will have a glitches in our output. And if you want to remove the glitches, you have to use the master slave flip-flop. This is the first thing that I want to clear here. Now we will move to the second important point, is the relation between the master slave flip-flop and the negative edge triggered flip-flop. You can see the master slave flip-flop's output is same as the negative edge triggered flip-flop's output. So I can say the master slave flip-flop work as a negative edge triggered flip-flop. So these are the two things that we have drawn from these waveforms, and they are very important. You have also learned how to draw the waveforms for the output of a D flip-flop. So it's already a very good lecture for you. You have learned so many things. If you have any problem regarding any point in this presentation, you can ask in the comment section. I will end this presentation here because I think we are crossing the time. So let's stop it here. See you in the next presentation.
Okay. So faham master and slave? Okay. Okay, sebab dia lagi satu, yang mana satu master, yang mana satu slave. Kau kena tahu to differentiate between that Okay. Any more question? So have you done with the video presentation for the lab? Bila nak siap? Because we don't have any more lab after this. So you will have to present so masa ni nanti lab. Okay, next week tengoklah sama ada you present ataupun saya tengok punya YouTube je. Kalau saya ada masa, saya suruh present. Kalau tak ada masa, okay, saya tengok punya YouTube tu je lah. Jadi buat elok. Okay, any more question?
So scared.
Apa subjektif? Test? Yelah, ini juga semua all those tak ada multiple choice ABC, tak ada. Multi-sim tak ada. Tak ada. Tak ada multi-sim. Okay? Okay, so
Doctor, before end, can I ask for the master slave D flip-flop?
You ask about what?
Master slave.
Yeah.
Just now from the timing diagram, the lecturer have four outputs, right? The QM, QS, QP, and QN. The master slave, yes, there is a glitch, so we use the master slave D flip-flops to avoid have a glitch, so we get the output of QS, is it? Then lastly, I heard he said what is
Okay. Because the first one is just it's a latch. It's refer to when D Q equal to D when the clock is high. The first two waveform timing diagram.
the QM and QS?
Yes, the below one is referred to the age. If you listen carefully, what he mentioned at the earlier section of the video, he did mention that refer to the age, the negative age, if I'm not mistaken. Okay. Okay.
Okay.
Any more question? Cepat awak, saya nak order untuk mak saya makan ni. Saya lupa nak order makan mak saya ni. Okay. Mak saya dah telefon tadi. Saya tak ingat sungguh. Okay. Okay, see you next week Next week ada quiz Okay, bye.
Thank you.